In this module, we are going to derive the integral momentum equation starting from the first principles. So, we are going to use the definition of displacement thickness and momentum thickness that we saw in the previous module. So, the derivation is having the same assumptions as was there for the boundary layer: steady, incompressible, constant viscosity, laminar flow, two-dimensional boundary layer. So, steady, two-dimensional, incompressible, viscosity is constant, and laminar. So, these were what was used for the derivation of the boundary layer equation or simplification of the boundary layer equation from the Navier-Stokes equation. So, continuity equation is du by dx plus dv by dy equal to 0. This is nothing but our continuity equation. X momentum equation is given by u du by dx plus v du by dy equal to minus dp by dx or minus 1 by rho dp by dx plus nu d square u by dy square. Then minus 1 by rho dp by dx becomes plus u infinity du infinity by dx. This comes from the fact that the dp by dx is transformed to u infinity du by dx by using the continuity of the pressure in from the free stream. This was seen when the boundary layer equations were derived. So, I am just going to take that directly. So, this term is nothing but your minus 1 by rho dp by dx. This term basically becomes u infinity du infinity by dx. So, this can now be, of course, when we write a governing equation, we need to write the boundary conditions. So, let us write the boundary conditions. At y equal to 0, we always draw this flat plate. This is your delta as a function of x. We are going to do this derivation for a general case where Vw not equal to 0. What is Vw? Vw equal to 0 implies the case of a solid plate, solid flat plate, okay, non-porous, which means there is no mass flow coming in or leaving the plate in this direction. Vw less than 0, that is where velocity is in the negative direction, we call this suction. Vw greater than 0, we call this blowing. Suction is basically where you suck out the air or suck out the working fluid. That is used as a technique to reduce the boundary layer thickness. Vw greater than 0 is where you blow into the boundary layer. So, you do that to increase the boundary layer thickness for certain specific applications. Porous medium, porous surfaces, you have porous wall, you definitely would have mass transfer in either into the boundary layer or out of the boundary layer, and that is given by Vw not equal to 0. So, our boundary condition in undergrad heat transfer, undergrad fluid mechanics was u equal to 0 at the wall, v equal to 0. While deriving this integral momentum equation, we will take that Vw not equal to 0, derive this equation u infinity varying with respect to x, which is also a general case, okay. In flow over a flat plate done for undergraduate students, we will make these two terms go to 0, that is u infinity is constant, okay. If I make it for a flat plate specifically, then I cannot use this integral equation for flow around a cylinder where u infinity could be changing, okay. Or if I go through a situation where I want to use the momentum equation for porous wall problem, then I will have to rederive this. So, this derivation takes care of u infinity not equal to constant given by this du infinity by dx term being there and Vw not equal to 0. So, you might want to just put a note here I do not use red pen much, but I am just going to write here. So, VW not equal to 0, general case, and u infinity is a function of x. This is also a general case. Flow over a flat plate, we will derive this with this and then put these terms to constant and VW equal to 0. We will do that. So, boundary conditions, y equal to 0, u is equal to 0, that is at the wall, u equal to 0, v equal to VW, which incidentally can be positive, negative or 0. This is the first boundary condition. Second boundary condition, at y equal to some capital H, u is equal to u infinity, v is equal to v sub h. What is this h? This h is somewhere here, way above. So, this is your y, h is somewhere there. Okay. So, h is much greater than delta max. Why I am writing delta max is, I have two deltas, right? I have delta, delta t. So, delta max refers to maximum of these two, whichever is bigger, whether the hydrodynamic boundary layer is bigger or in thickness or the thermal boundary layer is larger in thickness, this h is some location way above it. What is V sub h? Remember, there is a mass flow coming out. V is, you have u of x comma y inside the boundary layer, therefore, you have v of x comma y also. That means, at the edge of the boundary layer you have some y velocity, and if I am going to have suction and blowing, that may also be at a maybe increase. This V sub h is basically a velocity in the y direction at this so called imaginary plane at a location h far away from the wall. This delta max is basically larger of the delta or delta t, and h is much greater than that. Do not worry too much about this h, it will eventually drop off, it is just taken for this derivation purpose. So, x momentum equation, if I rewrite the x momentum equation now in a form which I like, I will write this as d by dx of u into u plus d by dy of v into u. What is the left hand side looking like? Left hand side is nothing but u du by dx. How do I get that? I get it directly from here, u du by dx plus v du by dy. Additional term comes in by the expansion of the first one, which is nothing but u du by dx again, u dv by dy. What about this? Continuity, this is identically 0. So, I can replace the left hand side of the momentum equation by this term, replaced using this. Okay. So, my left hand side of the momentum equation therefore is going to become d by dx of u times u plus d by dy of v times u is equal to u infinity du infinity by dx plus nu d squared u by dy squared. This is your x momentum. Continuity remains the same, du by dx plus dv by dy equal to 0. What I am trying to do here is, now I will integrate this. So, I will integrate the continuity equation from y equal to 0 to y equal to some capital H, which is way ahead or way above the boundary layer thicknesses. So, integral 0 to h du by dx with respect to y plus integral 0 to h dv by dy with respect to y equal to 0. This would mean this is integral 0 to h du by dx with respect to y plus integral dv by dy with respect to y would be nothing but v. V evaluated at h minus V evaluated at the wall, correct. This is nothing but VH minus VW. So, V evaluated at the wall is nothing but VW. Therefore, I can write VH minus VW is equal to minus d by dx of integral 0 to h u dy. I am taking the liberty of changing the order of integration and differentiation. So, h is not a function of x, okay, it is just some layer which is way ahead. So, it is not going to be affected by h at all, and therefore, I can take this h as a constant and pull out the differential out of the integral sign. Now, this is your integrated continuity equation. Let us keep this aside. We need the integrated momentum equation which we are going to do. So, this is my momentum equation, I am not rewriting this, I will take this and integrate it. So, momentum equation on integration, integral 0 to h d by dx of u dy plus integral 0 to h d by dy of uv dy is equal to integral 0 to h u infinity du infinity by dx dy plus integral 0 to h nu d squared u by dy squared dy, d squared u by dy squared dy. So, this one d by dx of 0 to h u dy plus integration of this is u times v evaluated at h, the product evaluated at h minus the product evaluated at the wall. Is that right? That is this term. Right hand side is nothing but u infinity, not a function of y, du by dx also can come out, and this can be h minus 0. We will probably change this back to this, and second term, second derivative on integration becomes the first derivative du by dy evaluated between the limits 0 and h. Okay. So, this is going to be simplified as follows. This quantity u is 0 at the wall, no slip condition. So, this term goes to 0. This therefore, integrated equation becomes d by dx of 0 to h u dy plus Vh. What is the x component of velocity beyond the boundary layer? It is nothing but u infinity. So, u becomes u infinity. In this limit, u was 0 at the wall, v is non-zero. Either way, this is going to drop off. Right hand side is nothing but u infinity h du infinity by dx plus nu du by dy at h minus nu du by dy at the wall. U is equal to u infinity, therefore, du by dy is 0. What is this quantity? Tau wall is equal to mu du by dy at the wall. Therefore, du by dy is nothing but tau over mu and nu. Mu by rho is equal to nu. So, I can substitute that, and therefore, I would get d by dx 0 to h u dy minus u infinity h du infinity by dx is equal to minus Vh u infinity minus, put these two here, you would get tau wall by rho. Okay, tau wall by rho. Okay, substitute for Vh from continuity equation. I had this quantity VH is VW minus this, I substitute that here. So, I would get d by dx of 0 to h uu dy minus u infinity h du infinity by dx minus, substitute for VH is nothing but VW minus d by dx 0 to h u dy times u infinity minus tau wall by rho, minus tau wall by rho. This, on simplification, we have to do the maths, unfortunately, we will just do it quickly. So, this is u infinity h, so on and so forth, we will write term by term. This is d by dx of uu dy going from 0 to h minus u infinity h du infinity by dx. You have minus of minus is plus, that when you bring this side will become minus again. So, you will have minus u infinity d by dx 0 to h u dy is equal to minus tau w by rho minus u infinity vw. Okay, I have just kept this side and brought this quantity here. That is what I have done. Okay. So, now let us look at this term. So, consider these manipulations would have been done by people over time. So, I am just going to write, consider d by dx of u infinity dy 0 to infinity. This is nothing but differentiation by parts. So, you would get du infinity by dx 0 to infinity u dy plus u infinity comes out as it is d by dx of 0 to infinity u dy, right. So, this is what is going to be used. So, I will write now this as d by dx of 0 to infinity uu dy. What am I, why am I going to use this? This term is there. Okay, where is this going to come? Du infinity by dx u dy, okay, du infinity dx u dy. So, I have a product term here which is going to be manipulated. So, if I look at this way, d by dx of uu dy remains as it is, d by dx of uu dy remains as it is, right hand side remains as it is. So, I will just call this RHS and continue writing it that way. These are the two terms that need to be taken into account. This is nothing but du infinity by dx as it is u infinity dy. So, I will write the second term as du infinity by dx 0 to h u infinity dy, right. U infinity can come out, dy integral is h minus 0. So, h. So, the second term has been just manipulated like this, first term remains like this. This term, which I am going to circle this here, this term is going to be manipulated using this identity. U infinity d by dx of u dy is written here, that is going to be used, this identity is going to be used. So, minus of open bracket d by dx of integral 0 to h u infinity dy minus du infinity by dx integral 0 to h u dy equal to right hand side, that nothing is changing. So, I have substituted for this term using this identity. Now, you will wonder, suddenly there were partial derivatives and they have now become regular derivatives. How is it so? That is happening because certain quantities are only a function of x. How do I know that? This d by dx of u dy, this quantity uu dy, u is a function of x comma y. when I integrate with respect to y, it is only going to be a function of x. Therefore, this derivative u is a function of y, integral of u is therefore going to be a function of x only. Integral u dy is only a function of x. Therefore, this is going to become d by dx of u dy 0 to h minus du infinity by dx 0 to h u infinity dy minus d by dx of 0 to h u infinity dy minus du infinity by dx integral 0 to h u dy equal to right hand side. Okay. Now, where does this lead me? I will group these terms, the one in green and these two are going to be grouped. So, if I group this terms, I will get d by dx of 0 to h u times u minus u infinity dy plus du infinity by dx du infinity by dx, yeah, this is a plus here, sorry, minus into minus is plus du infinity by dx integral 0 to h u dy minus u infinity dy, sorry, u minus u infinity dy equal to right hand side. Okay. So, we are almost done with the integral equation. So, I will now multiply and divide by quantities such that I go back to my definition of momentum and displacement thickness. I have momentum and displacement thickness given like this. So, in this expression I have u minus u infinity. So, I want to get this. So, if I divide both this term by u infinity squared, I will absorb one u infinity here, another in this bracket. I can't just divide, so I have to multiply also. Here I divide and multiply by u infinity such that I get the displacement thickness. That is the manipulation I am going to do, and when I do that, so I multiply and divide appropriately, I get d by dx 0 to h u infinity squared u by u infinity 1 minus u by u infinity dy plus du infinity by dx integral 0 to h u infinity u by u infinity minus 1 dy equal to right hand side. And what I am left with is just manipulation of this equation. U infinity, this one is just going to be, I am going to replace this by definitions of theta and or theta or delta 2 and delta star. Keeping that in mind, I will get d by minus d by dx. This is going to be du infinity by dx. So, I am going to write this as d by dx of u infinity squared delta 2. Okay. The right hand side had a minus sign, let us just come back to that slowly, plus du infinity by dx u infinity times delta star, this is delta star, this is your delta 2 is equal to minus v w u infinity minus t tau wall by rho. So, I absorb the minus signs here. So, I am going to write this as, so I would get this as, this turns out to be minus minus. So, I would get d by dx of u infinity squared delta 2 plus u infinity du infinity by dx delta star is equal to v w u infinity plus tau wall by rho. Divide through u infinity squared and use Cfx is equal to tau wall by 1/2 rho u infinity squared. If I do this, I would get this as u infinity squared by u infinity squared d delta 2 by dx plus delta 2 comes out 2 times u infinity by u infinity squared du infinity by dx, product rule. This one would be u infinity du infinity by dx delta star as it is, Vw by u infinity, one u infinity cancels with the second one, so you are left with one u infinity, tau wall by 1/2 rho u infinity squared. U infinity squared I am going to have, so this is going to be Cfx by 2, Cfx by 2. So, this term was opened into two terms, u infinity squared d delta 2 by dx, delta 2 comes out 2 u infinity, divide by u infinity squared, one of them will cancel, du infinity by dx. This one as it is, u infinity by u infinity squared, one of them will cancel off and the right hand side remains as it is. Therefore, I can write this as d d2 by dx plus 1 by u infinity du infinity by dx 2 delta 2 plus delta star is equal to Vw by u infinity plus Cfx by 2. Coefficient of friction is what is needed by us. So, the Navier-Stokes equation, which was a partial differential equation, now has become some kind of an ordinary differential equation with the independent variable being only x, the dependent variable being delta 2, which is a physically important quantity, which is the momentum thickness. This is a very general equation where Vw was non-zero, du infinity by dx was non-zero, that means varying free stream velocity. For flow over a flat plate typical of undergraduate curriculum and a solid plate, these two terms would drop off and we would get d delta 2 by dx is equal to Cfx by 2. In the next module, we will see how to use this von Karman equation to get the boundary layer thickness. Whatever we have seen in similarity method, we will get a slightly different constant here, but it is a lot easier method to follow. Thank you.